Hey everyone, in this video we are going to be covering the topic of pedigrees. So a pedigree, this chart here shows you what a pedigree would look like. It's really just a family tree that is very simplified. It takes a lot of the detail of a family tree out. And what we're doing is we're tracking one specific trait throughout a family. So instead of using pictures of family members and whatnot, we use just shapes and symbols and shading to represent that trait we are tracking. So let's go through and talk about what the different shapes, symbols, color, shading, all of that represents in this pedigree chart. So first off, here's a really simple pedigree. And the shape of a square in a pedigree represents a biological male, meaning they would have the X and Y chromosomes if we talk about those sex chromosomes. So squares are males. Circles then represent biological females. They would be individuals with two X chromosomes. So square, male, circle, female. The shading in a pedigree represents the trait that we are tracking. So individuals that are unshaded in the pedigree, they are non-affected, meaning they do not have the trait that we are tracking. For individuals that have a shaded in symbol, that means they are affected with the trait. They have the trait that is being tracked in this pedigree. Carriers are sometimes shown on a pedigree, but not always. So sometimes you will see half shaded in symbols, and that represents carriers. And because carriers are female, they should only ever be half shaded in circles if we are tracking a sex-linked trait. Now, it doesn't have to be a sex-linked trait. It could be a regular trait as well. So then you might see half shading in the squares for males. So carriers would be those heterozygous genotypes. But there are pedigrees that do not use the half shading. So be aware that sometimes half shading is used for heterozygous genotypes and sometimes it's not. If you see a line connecting two individuals, we would represent that as a mating line, meaning that these two individuals have children together. And generations would be separate rows in your pedigree. So pedigrees are meant to be pretty organized. So generation 1 we see up here at the top, and we usually use Roman numerals to represent the different generations. And then the next row of symbols would be the next generation, so the offspring of that first generation. When we see the children of a mating pair, those siblings would be connected to those parents, and the siblings would be put in birth order. So the square here represents male. This male would be first in the order here, so that would be the firstborn. Then we have the middle child, and then the youngest offspring here. So the children should always be listed in birth order. All right, so just a little bit of practice here. So if we're looking at this particular pedigree, so it says, is person number 3 in generation number 2 male or female? So we need to first find generation number 2, which again, we use Roman numerals typically to represent those generations. So this second line here represents generation 2, and it's asking about person number 3. So that would be this individual here. It is a shaded in square. So that tells me, because it's a square, that this person is a male. They have an XY chromosome. Let's do some more practice. So are individuals 5 and 6 in generation 3 siblings, or are they mating? So we need to find generation 3. That is this last row in this pedigree. And we're looking at individuals 5 and individuals 6. So it's asking, are they siblings or are they mating? So if they're if they're mating, there should be a line connecting the two. Whereas if they're siblings, they should have lines coming out from parents of the previous generation. So what we see here is that there's not a line connecting 5 and 6 together, but instead there are lines coming out of the top of each of them going up to a mating line in the next generation. So that tells me that individual 5 and 6 in generation number 3 are siblings. And a little more practice, is individual number 2 of generation number 1 affected or non-affected by the trait? So generation 1 is our top row here. Individual number 2, they are shaded in. So that would tell me that they are affected by the trait. They have the trait being tracked in this pedigree. So that should help you get a little bit of overview of the symbols and the shading that are used in pedigrees and how to just read them. Now let's get a little bit more into the traits and types of traits that we are going to be tracking in these pedigrees. So the first thing that we need to understand is the type of trait being tracked. So there are 2 types of traits that we're going to be, or 4 kinds of traits, I guess, that we're going to be tracking in these traits. So there's 2 kind of questions that we need to ask. The first question we want to ask, is the trait that we're tracking in this pedigree a dominant trait or a recessive trait? Which means, is the trait showing up when you have one dominant allele, or are we tracking a trait that shows up when you have the 2 recessive alleles? So if we see that the affected individual, there is an affected individual in every single generation of this pedigree, then it's a dominant trait. It's showing up generation after generation. If we see that our trait is skipping a generation, it doesn't appear in every generation, then it's most likely going to be a recessive trait. It has that ability to skip. So that will tell us right then and there if we're dealing with a dominant trait or a recessive trait. We also need to know, is the trait that we're tracking an autosomal trait, meaning it falls on chromosome pairs 1 through 22? Or is it a sex-linked trait, meaning the trait is found on our sex chromosomes? So there's kind of 2 different ways we can figure this out. First is, do we look and see that the trait being tracked is affecting males and females equally? If so, it's probably an autosomal trait, right? It affects everybody. It's not just affecting males, not just affecting females. Whereas if we see that the trait that is tracked in the pedigree is more common in males, then we're most likely dealing with a sex-linked trait. And that is because our sex-linked traits are typically on the X chromosome. Females have 2 X chromosomes, males only have 1. So it is a lot easier for males to get those sex-linked traits because they only have 1 X chromosome. So we'd see those traits show up more likely in males. So by asking these questions and kind of going through this little flow chart here, we can figure out what type of trait we're tracking. We can figure out, is it dominant or recessive? Is it autosomal or sex-linked? So let's practice this. So first off, I have pedigree still here. Is the trait that we're tracking here a dominant trait or a recessive trait? So I notice that I see it appear in generation 1. I see it appear in generation 2 multiple times. From the children of generation 1, there are 2 children that have it. And then in generation 3, we have 2 children here that both have it from this individual parent. And then we also see another child having it. So this trait does appear in every single generation. So that tells me right there that this must be a dominant trait that is being tracked. So then now I want to figure out, is this trait an autosomal trait or is it a sex-linked trait? So autosomal meaning it falls on your, I don't want to say regular chromosomes, but chromosomes numbered 1 through 22, or is it on the pair of sex chromosomes? And so to figure that out, I got to look at the distribution of the trait in males and females. So I see 3 females affected by the trait, and I see 3 males affected by the trait. So because it seems to appear in both males and females pretty equally, this is an autosomal trait. It is not sex-linked. So now the tough part with pedigrees is going through and determining genotypes. So now that we figured out what type of trait we're dealing with, I want to go through and be able to label the genotypes of every individual in my pedigree. So we're going to go through this step by step. So I have a pedigree here that has 3 generations, and I have my key up here showing me males versus females and who has a trait versus doesn't. So the first step is to figure out in this pedigree, is the trait autosomal or sex-linked? Okay, so before we just started looking at this problem, we talked about if it's autosomal, it should be in both males and females pretty equally. If it's sex-linked, it should be in males more so than females. So looking at my pedigree right here, I see 2 females affected and 2 males affected. So that tells me that I'm dealing with an autosomal trait. If I was dealing with a sex-linked trait, I would go ahead and add the sex genotypes to every individual. But because I do not have a sex-linked trait, I'm going to move on to the next step. I don't have to worry about X's and Y's because this is not a sex-linked trait. It is autosomal. So I'm going to move on to the next step. So step 2 says determine if the trait is dominant or recessive. So I'm looking at this pedigree. I want to see, does the trait appear in every generation or does it skip a generation? So I see that generation 1 does not have the trait, but it appears now in generation 2 and in generation 3. So that tells me I must be dealing with a recessive trait because it does not appear in every generation. So I know that my trait is autosomal and I know that it's recessive. So now that I have that information, I need to go through and label the recessive individual's genotype. And they must have 2 recessive alleles because they're recessive. So again, no X's and Y's because I'm not dealing with a sex-linked trait. So I just need to go through and label every individual that is recessive. So anyone that is shaded, they must be recessive because that is the trait we are tracking. We're tracking an autosomal recessive trait. So like for example, number 6 in generation 2, they must have the recessive genotype. So I'm just going to use the letter H here. You could use any letter because I don't know what this condition is. So person 6, 8, 11, and 13 are all shaded. Because we're tracking a recessive trait, we know that they must have both recessive alleles. Okay. So step 4 is the rest of the individuals must be dominant. So they must have at least one dominant allele. So I can go through and for everyone else put dominant alleles in, but only one. I don't know if those individuals are big H or big H, little h. So the next step would be to determine if these dominant individuals are heterozygous or homozygous. I'm going to need to use Punnett squares to figure out. It's kind of like a puzzle if they're big H, or big H, little h. So for individuals 1 and 2, I have 2 possible scenarios here. They're both unaffected. So I could have, a big H crossed with big H, little h. Okay, so I'm saying like person number 1 is big H, person number 2 is big H, little h. I fill in my Punnett square. Of the offspring, there's a 100% chance the offspring are all dominant. A 0% chance that the offspring are recessive. I know that that combination of parent genotypes cannot work because I have offspring here, number 6, individual 6, little h. This Punnett square does not get me little h whatsoever. So this Punnett square, where I have both parents here, number 1 and 2, as big H, little h, I get mostly dominant offspring, 75% chance that the offspring are dominant, but I have a 25% chance of offspring being little h. So this is the most likely scenario here. I didn't even do big H across 1 and 2 because I know if both parents were big H, all the offspring had to be big H. Like it's not even a possibility for them to be that because I have an offspring little h. So I know parent 1 and parent 2 have to be big H, little h. It's the only way they have an offspring number 6 that is little h. Okay. So now I know I can add that in. So it is more likely that they're both big H, little h. I've filled that in. So I'm going to repeat this process for the remaining individuals. So out of their children that 1 and 2 had, 4, 5, and 6, we know 6 is little h, little h. And we know that the parents were both, big H, little h, big H, little h. So now we got to figure out the other individuals here. And so if I look at 6 and 7, which is more likely to have 7 be big H, or big H, little h, looking at the children that they have together. So if the number 7 was big H, 100% of their offspring would also be big H, little h. Is that what I see in the pedigree? No. If I have the number 7 be big H, little h, there's a 50% chance the offspring are big H, little h, and a 50% chance that they're little h, little h. So now I figured out that, and I'd be able to fill it in. So now you would just literally repeat this process for the rest of the individuals in this Punnett square. I'd be able to go and figure out 5, 4, and so on. So I'm not going to go through and finish this pedigree. I'd like you to take the chance to finish it for yourself and get some practice doing the Punnett squares and filling in the genotypes. But I have linked in the Amoeba Sisters video here for you to watch on your own. It does a really good job going through pedigrees and figuring out those genotypes using Punnett squares.